Hello, Physics Nation. My name is Nate Larmond, and my apparatus literally fell apart at the end of my last video, but everything's back up and running. I think everything's cool. We're actually going to move to quantitative analysis. We're going to take a look at the actual force in newtons that is being pulled down on this side. We're going to call this side the input side. This is the low force side. And we're going to compare that to the force on the output side. This is the load side. This is 6/4, and this is 2/4 and a nickel. And that's where we were, like I said, when I think the heavy guy, the load, just fell off. So hopefully my tape is fast and secure and we won't have any equipment failure. So like I said, we're going to do some quantitative comparison. I have 2/4 and a nickel over here and 6/4 over here. So coins are mass standards. That's why we use them as weights in our quarantine at-home lab experiences. Except this page looks kind of busy. I mean, it gets us there. We're basically accountants of energy. We're going to keep track of how much energy we put into the system and how much energy we get out of the system. Except I thought my first attempt was kind of busy. There was a lot going on there, so I did a second attempt. And like I said, accountants keep track of money. Money can flow in, money can flow out, but it doesn't just appear and it doesn't just disappear. Likewise with energy. We are accountants of energy. When I apply this force through this distance right here, I'm dumping energy into the system. So I'm just pretending it's this weight, that is the weight of 2/4 and 1 nickel. Where are we? Right here. That's 16.3 grams. That weighs about 0.16 newtons, or 16/100ths of a newton. And the whole point of the first two videos was to demonstrate that, yeah, it's a small force, but you have to apply that force over 3 times the distance. Look how much string I have to move in order to lift this load right here. All right, so this guy moves 30 centimeters. Every time this guy moves 10 centimeters. We have a 3-to-1 distance ratio going on here. All right, so that's what we're accountants of. We're accountants of energy. Newtons times meters are joules. So 0.16 newtons multiplied by 0.3 meters, that's 0.05 joules, 5/100ths of a joule. Okay? Then we keep track of what we get out of this system. Well, as I do work over here, the load goes up. It is gaining gravitational potential energy, or output work. We don't have to include the Earth in our system. We can just say gravity is an external force, and therefore, if this load goes up and gravity is down, it's doing negative work. All right, gravity is stealing energy from the system, but most people don't look at it like that. Most people sort of envelop the Earth in the system and say, we are gaining gravitational potential energy by inputting work on this side. So how much gravitational potential energy? Well, 6/4, let me see, has a mass of 34 grams. That weighs 0.34 newtons, roughly a third of a newton. And remember, if you put in 30 centimeters here, it only goes up 10 centimeters on the load side. So that's how many joules we are getting out of this system. And here's our little accounting exercise. What do you get out divided by what you put in? So 0.034 joules was the stored potential energy, and we put in 0.034. Well, it's not so great. That's only 2/3, roughly. That is, we get out 2/3 of the energy we put in. Where's the energy go? Well, this guy. He's the most likely suspect. See, we have some pretty small masses, 34 grams, 16 grams. You know, the mass of the apparatus is significant compared to the mass of our input force and the mass of our output force. So we're wasting a lot of energy, about 1/3 of the energy we put in, but it's actually going to lifting the load. The point of the machine is to multiply force. We're applying 16 grams to lift 34 grams. A mechanical advantage of 2. Happy crafting. See you in the next video.